Hello everybody, welcome to the Neo4j online meetup. So for those of you keeping count, this is meetup number 29. And I'm joined today by Sun, who you can hopefully see on the video as well. So Sun is going to be talking to us about comparing large 3D city models in CityGML using Neo4j. So I came across Sun's project a couple of months ago while searching on GitHub for Neo4j projects, and looked pretty interesting. For those, so I'll just do a quick bit of housekeeping, and then I'll hand over to Sun. So for those of you who haven't joined us before, Sun's going to be showing us some code in his presentation. So you'll need to make sure your resolution is set to one where you can see it clearly. So in the bottom right-hand corner of your YouTube screen, you'll see a little HD icon. If you click that, make sure your quality is set to 720p or higher. With that, I guess I'll introduce Sun, and maybe you can explain what you're going to talk about and a bit about yourself as well.
Thank you, Mark, for the introduction. Hello, everybody. My name is Sun Nguyen, and I'm a researcher working at the Technical University of Munich. And I'd like to talk about the master thesis that I've done in the summer. And I also presented this topic in the 3DGeo Info Conference in Melbourne last, I think 2 weeks ago. And perhaps I can select this share screen now, right?
Yeah, so I guess before you get started, I'll just I forgot to remind everyone, if you have any questions, you can either ask them on the YouTube chat on the right-hand side of the window, or Sun if you have any afterwards that you think of, you can ask them in the Neo4j Slack in the Neo4j online meetup page. Cool. Anyway, I will give you the power to present.
Okay. So, cool. See it now?
Yeah, cool. We're good.
So I'd like to talk about the spatial-semantic comparison of large 3D city models in CityGML using a graph database. Okay, see it now? Okay,
Yeah, I can still see it now. It's good.
Okay, so it's about gender detection, which is very important in city modeling. For example, a city may have multiple 3D city models encoded in CityGML and recorded at different times. So this makes the analysis of the city's evolution over a given period of time more difficult. Another example is about tracking collaborative changes to an existing city model. Conflicts may occur if the current user is unaware of changes previously made by other users. So for such use cases, the ideal solution is to compare and detect changes between city models, which are mostly encoded in CityGML. But unfortunately, up to now, we don't have any tool that is fully capable of such tasks between CityGML models. And as a result, older models often are completely overridden with newer ones, which causes not only many unnecessary transactions, but also loss of extended semantic data. So why is it so hard to match to CityGML datasets? Well, here are some of the main challenges we faced. CityGML defines very complex object hierarchies. CityGML objects can be represented in various syntactic ways, such as inline or X-link objects. CityGML objects can occur in different orders in the file. CityGML allows for geometric ambiguities. For example, a polygon can be represented by a single ring or by a set of smaller rings. CityGML datasets can be very large in size, from several gigabytes to terabytes, and objects within a CityGML dataset build a complex graph. So all of these can be solved using our solution. So we represent CityGML as graphs because basically CityGML datasets are graphs. Using graphs can also solve syntactic ambiguities between inline and X-linked GM objects. Graphs and graph algorithms are naturally suitable for big data. Although mapping CityGML onto graphs is not new, but it hasn't been fully addressed yet. So we employ the graph database Neo4j to take full advantage of CityGML's graph structure. Because Neo4j can also store process information offline for later use. And we also make full use of the high performance query functionalities of the graph database Neo4j to perform comparison process.
So can I ask a quick question for you, for anyone like me who doesn't know what CityGML is? Is CityGML is it like a custom markup? Is it XML based, or how would you describe that?
Yeah, CityGML is an open standardized data format for storing and exchanging 3D city models like cities and landscapes. It is an application schema of GML3, which is again an extension of XML.
Okay, cool.
Thank you for the question. Yeah. Okay. So this is the workflow of our implementation. So basically, it is divided into 3 major steps. The first step is to map input CityGML datasets onto graph database. So we have on the left side here the old CityGML dataset, and on the right hand side the newer CityGML dataset. So we map both of them in the graph database in the first step. And in the second step, we match these graphs together. And in the last step, we update the LCD model. So let's go to the first step, mapping. In order to deal with very large CityGML datasets, we divide them into smaller pieces. Each piece is a feature like a boundary surface, such as ground or wall surface, or a top-level feature like a building. We then convert each piece, each feature, to Java objects using the library CityGML4j. In the second step, we map these Java objects onto graph components using the Neo4j Java Core API. So one major problem we have to face is that you already know Neo4j graphs are value-based, which means Neo4j can only store key value pairs and relationships. It doesn't provide subclassing and inheritance mechanism. So to overcome this, we developed a brand new approach to mapping Java objects onto graphs based on their class hierarchy. We start with a container graph node, storing the contents defined in the lowermost Java class in the hierarchy. And then we successively expand the container node with the contents of each superclass while moving up the class hierarchy. So this way, the implementation is efficient. The resulting graphs are very compact, and there is minimum to zero information loss while mapping. So this is an example of how it works for the building object. So at the top, you see here, this is the class hierarchy of the building class. So for the building class, we create a container node, which is shown in green here. And for the abstract building superclass, we expand this container node with the contents of this abstract building class. And for the other superclasses, we do the same. All of these shown in this yellow box here, they represent, they are the graph representation of the building object. So the second step is to match the mapped graphs. Things crafts, things crafts consists of nodes and relationships. So matching crafts reduces to matching their nodes and relationships. So here, for instance, I have node A and B. To match properties of node A and B is very easy because they are texts. To match single relationship is also simple because we only have one relationship for each node. But the real problem is now to match multi-relationships. Should I match A1 with B1? Or should I match A1 with B2 or B3? So city models can have many objects of the same type. Brute force comparing each possible pair is inefficient. So to reduce computational costs, we have to find the best candidate for each building first. So we do this by performing 2 rounds of tests. The first test is the topological test for spatial overlaps of buildings using an R tree over 2D building footprints. If the first round gives more than 1 candidate, we then perform the second round. In the second round, we match the candidates' geometries. So to match the geometry of buildings and building parts, we calculate the shared volume of these 2 buildings and compare it with the threshold, for example, 95% or so. If it exceeds this threshold, then we say, okay, these 2 buildings are matched with each other. For points, we have to bring these 2 points into the same spatial reference system. And then we match the coordinates considering the error tolerance, epsilon. Here on the right-hand side, for example, the blue point is matched to the yellow point because it's located in the neighborhood of the yellow point. On the other hand, this red point is not matched to the yellow point because it's located too far away from the yellow point. For line strings, we merge and consider all consecutive collinear segments given a distance tolerance as one big segment. And then we successively match geometry of start and endpoint. For linear rings, well, rings are in 2D planar, but they are arbitrarily oriented in 3D. So we have to rotate similarly oriented rings, given an angle tolerance to predefine 2D plane first, and then we compare or match their shapes regardless of order or number of vertices. For polygons, we subtract all interior rings from exterior rings, and then we match the shapes of polygons similarly to linear rings. So the last step is to update the old CityGML datasets using this graph database. So for each deviation found, we create an edit operation. For properties, we have 3 edit operations, namely insert, update, and delete property operation. For nodes, we have 2, namely insert and delete node operation. This is an example of how an edit operation looks like in Neo4j. At the top, you see the root of all edit operations. The green node is an edit operation attached on the fly while matching. The yellow node on the left is the node from the older model, and the yellow node on the right is the node from the newer model. So all of these edit operations can be employed by various services to update old CityGML datasets, such as using the transactional web feature service. So here are the results that we've been experimenting so far. The test system has SUSE Linux Enterprise Server operating system, and it is equipped with a 16-core hyper-threaded CPU. So in the first test case, we wanted to test how the program behaves against very large input data sets. So we used the entire 3D city model of Berlin, each of which contains about 540,000 buildings and is about 16 gigabytes in physical storage. So after the test is complete, we found 320 million nodes, from which we have 15.5 million services, 14 million points, 13 million polygons, and more than 1 million buildings. So the database is about 130 gigabytes big in physical storage. We also tested or calculated the runtime of this test case. So the blue bars are the runtime of the mapping process. The yellow bars are the runtime of the matching process. And ST stands for single-threaded, XPYC stands for X producers, and Y consumers. Well, they are then multi-threaded, because the testing CPU has 16 cores. So we found out that using the configuration 1P15C results in the most efficient runtime. The mapping process takes less than 64 minutes to complete, and the matching process takes then less than 16 minutes to match approximately 32 gigabytes of data. It means 85,000 nodes while mapping and per second, and 340,000 nodes per second for the matching process. In the second test case, we use the same test environment, but we use different input datasets. We use the old and new dataset of Berlin Moabit. The old dataset has approximately 1,100 buildings, and the second dataset has 12,3 thousand buildings. So here you can see on the left-hand side, this is the old Berlin Moabit, and the new Berlin Moabit is on the right-hand side. So the older CityGML dataset is much smaller than the new one, so we expect many deviations. The test takes less than 3 minutes to complete, and we found more than 170,000 deviations, of which we see 11.2 thousand new buildings, and 40 buildings are deleted from the older model. So in conclusion, in the mapping process, large CityGML datasets can be mapped to graphs completely. Syntactic ambiguities are solved in the process. In the matching process, created graphs are matched with respect to their semantic and geometric properties. Topology is used to accelerate query time. And in the last step, edit operations are attached on the fly to detect the deviation sources and are employed by the WFS, the transactional web future service, to update city models. So for the future, we plan to implement for further CityGML modules, such as bridge, tunnel, transport, etc. And we also plan to use this graph presentation to analyze CityGML datasets and craft querying reasoning tools. It is also possible to use this implementation to support collaborative work in editing and updating 3D city models in CityGML, providing checkout, check-in tools for 3D City DB. So if you are interested in our projects, you can visit us on our homepage, github.com/tum-gis. And finally, I can have prepared 2 small demos that I'd like to present now. Okay, so let's this one. So this is the README file of my GitHub page. So if you are interested, you can read my master thesis here or our paper here. I also explained some of the most important points here in the README file. So, for example, how to run it on your local machine and how to read the results. Okay, so in the first demo, I'd like to show you how the program matches two buildings. So these two buildings are identical except for these properties. So this is how CityGML looks like. So for this newer building, I changed this one from 22nd of February to 26th of February. And then I moved this line somewhere down here. Here, for example, under measure type. So, and save. And then I can run the program here in the command line. Okay, let's see. So as you can see here, okay, let me scroll up. Okay, so before the test, the program shows the configurations of this test case. So for my laptop, I have 4 cores, and this is these are the configurations for the mapping, the matching, and the updating process. So, and here are the logs for debugging purposes.
Can you quickly explain the difference between the mapping and matching processes here?
The mapping, well, in the mapping process, the input data sets are mapped onto graphs.
Okay. And then the matching is comparing the two graphs against each other.
Yeah.
Cool.
Yeah. So at the end of the test, we have a very nice table. So this shows how many nodes we have and how many types of nodes we have here. Also, if we find any deviations, they will be listed here. So here we found one deviation, and this is the update property edit operation. So I can go back to the export folder. So this table edit operations.csv shows all the edit operations found or created. So we only have one edit operation here. And the type of this edit operation is update property. So we go to the table, update property. So this one here. So we see here the old value is 22nd of February and the new value is 26th of February. So it was correctly detected. So I also can visualize it in Neo4j. So just start this database and go to.
So those CSV files with changes, you pass those to the Java program that then runs them through the Java API and changes the graph.
I'm sorry.
Those CSV files that get created, are they then processed by your program and they do the changes in the graph?
Yeah. So while matching to graphs, well, if a deviation is found, I attach an edit operation to the deviation source. And at the end, when the program is complete, I then rerun, or I then, because I have a root node that is connected to all edit operations. So I can query this one to get all the edit operations and export them into CSV data, CSV files.
Okay.
Yeah. So, but because It's very hard if we have many deviations or edit operations. It's very hard to test if they are correct or not. So I just exported all of them into multiple tables here, so we can check them later. Does that answer your question?
Yeah. So okay. So that's basically like just a log of what's been done, so you can check.
Yeah, it's like
cool.
They are also divided into corresponding types. For example, edit operations that are about updating property will be listed here in the update property table. And for the edit operations that are used for nodes, we can see them here in the edit node table or the insert node table. And this table contains all of them. So it's like here in this edit operations, we have the edit operation ID, so we can look them up in the specific table. For example, here update property, then have to go to the update property and find the ID of this edit operation here. So okay, let's go to Neo4j browser. So this one here. Okay, I think I'm connected now. Close this one.
Let's put the password down just below.
Okay, I think I'm connected.
Oh,
cool. So okay, let's show all of the nodes. Let me zoom out a little bit. So these are the two graphs of these two inputted CityGML datasets. And I have to zoom in again. So the blue nodes are the building nodes, and the yellow nodes here is the edit operation. If I click on this node, you can see the building on the left is the newer building, and the building on the right is the older building. But if I click on this edit operation node, you can see here all the important information is stored here. The most important ones are old value, 22nd of February, and newer value is 26th of February. And this one points to the older building. So this older building has the older value of the creation date, and this shows that we should update this older building with the newer creation date property. So, but our program can do more than just comparing text. So in the second demo, I'd like to compare the geometry of two polygons. So I have in the first test, in the first data set, I have one polygon which contains one hole here. It's shown in white. So the polygon is in gray and the hole is in white. And in the second data set, I also have the same polygon, but now I have two holes. So geometrically, they are the same. Okay, and let's see if the program can detect it. Okay, let's go to, I have to stop Neo4j first. And then go to the command line. Let's take a test.
So is there like a GML representation of that, the difference in those two diagrams?
I don't understand what's, can you explain more?
So do you have two GML files, presumably one representing the one where there's one shape and one representing the one where there's two shapes?
Yeah.
Cool.
So here I can show you this one. So those are in CityGML also, because CityGML can also represent geometries. So this is the first one. It's also in CityGML.
Oh wow, okay, so it has all the coordinates in there.
Yeah. So the points are represented differently into CityGML datasets. In the first one, we have point property, and in the second one, we have GML post. So they are different, but geometrically they are the same. So okay, it's done. So as you can see here, we have 8 delete node operations and 7 insert node operations.
Yep.
Yeah, but if we carry out all of these edit operations, so the two CityGML datasets will be identical. But we don't have to do this because the program says all of 15 edit operations here are optional because the geometries of these two polygons are the same. So so we don't have to. But if we carry out these 15 edit operations, the datasets will be identical. So in
Interesting. Okay.
Yeah. So in Neo4j, let's start it again. Go back to this one. Okay, perhaps I should close this one. And should be the root of the matching process, and show all the edit operations. So the red nodes are the delete node operations, and green nodes are the insert node operations. So all of them are optional. As you can see here, it's optional true. So if I expand this node, we can see it is attached to a point. If I expand this node, it's attached to the linear ring and also to a point. Okay, so that was it. Yeah.
So why is that difference in the two buildings not considered a change? Because there was like a extra line, wasn't there? It's like, what was it actually doing? Was it?
Yeah, in the first test.
No, in the one where you did the two diagrams against each other.
Okay.
Showing the two shapes. Yeah, this one. Yeah. So there's like on the second line, there's like it's like it splits the shape in.
Yeah. So this one is a polygon or a ring representing a hole, and I have here for the same hole, but I have 2 rings or 2 rectangles. Yeah.
But in terms of the graph, those are equivalent.
Yeah, they are equivalent. Yes.
Okay. But in CityGML, they're different.
In CityGML, they are represented in 2 different ways. Yes.
Okay, all right. But we just treat them as being equivalent.
Yeah,
cool.
Because in CityGML, it is very flexible. It is the users have many choices. User can represent or can define a geometry in different ways. It is possible, but for developers or for programmers, it's very difficult because we have many geometric ambiguities. So so this program basically does is to consider these 2 polygons geometrically equal.
Yeah, okay, makes sense. So before we started, we were talking about whether you thought there were any lessons that could be applied for like general graph diffing. So you're obviously doing diffing of CityGML. Are there any things that, like, if people have their own graphs and they have like 2 versions of a graph, like I've got a graph from, I don't know, for example, a graph today and a graph from a week ago, and I want to know what has changed between them. Do you have any tips from your work that people could apply for that type of problem?
Well, technical tip or
yeah, technical tip.
Sorry?
Yeah, technical tip. Or anything. I mean, any tips.
Okay. So what I did is, well, I compare or I match the graphs from the top to the bottom. So I match the nodes, the root first, and then I match their properties. These nodes, and then I match their children nodes or the untried nodes or the relationships. And then for each pair of relationship, if they are the best candidates, I will recursively match them together with the same process.
Okay, cool.
Yeah. Well, of course, there are many challenges and difficulties we have to overcome. For example, in CityGML, we have so many types of objects and geometries. So you have a very huge or very large class hierarchy. And another challenge is because, as I mentioned in the slides, Neo4j is a value-based graph database. So normally, it will lead to information loss while mapping from Java to Neo4j. So we have to develop a new approach that will prevent information loss. And in fact, we managed to map Java objects onto graphs completely with minimum or zero information loss. So it's nice.
Cool. Did you have one more demo to go, or did you already finish with them?
Yeah, I think I've finished 2 of them.
Cool.
Yeah.
Okay, so if anybody has any questions, I guess now is your time to ask them either on Slack or on the YouTube chat. And just to remind you, if you liked the presentation, you found it interesting, don't forget to like it on YouTube so that other people can find it. And I guess there's a little bit of a lag on the questions, but if you're watching this afterwards or you think of a question later, you can always ask it on the Neo4j online meetup channel. So Sun has, you've seen it kind of, he's signed into Slack, so he can answer your questions on there. And do you want to put the link for the repository on the screen so that people can see where they can go if they want to have a look at some of your ideas? Cool. Otherwise, yeah. So I'll put the link for the GitHub in the comments then afterwards. And I guess thanks, Sun, for coming and talking about the project, and thanks everyone who joined us. We'll see you next time.
Thank you for having me.
Thank you. Bye.
Bye.